pleasure to introduce the next speaker, Dr. Arati Balagi, and we'll be speaking about scalability.
A very good afternoon, ladies and gentlemen. It's 2 o'clock in the afternoon, I know, and my slides are heavy on numbers. So sorry about that. But I'll do my best to keep you awake. Okay? So my name is Dr. Arati Baliga. I co-lead, along with another colleague of mine, the Blockchain Innovation and R&D Initiative within Persistent Systems. So let me start with a quick overview of Hyperledger Fabric. Fabric is an enterprise blockchain platform. It was one of the first platforms to release a production-grade version back in July 2017, followed by Multichain, Corda, and Quorum, which are some of the key players in the enterprise blockchain space. By consortium platform or enterprise platform, business entities can come together, contribute nodes to the blockchain network, and collectively maintain the blockchain, run smart contracts, and collectively maintain the state. So these nodes are essentially called peers in Fabric. Most of the peers play the role of committing peers, and a subset of them typically plays the role of endorsing peers. More on that on the next slide. Other entities that you find in Fabric are the orderer or the ordering service, which is typically responsible for ordering transactions and batching them into blocks. Clients are end devices, which run blockchain applications and initiate transactions on the blockchain. Smart contracts that run on the blockchain in Fabric are typically called chain code. Endpoints initiate transactions, which are invocation of chain code methods. Each chain code typically has some amount of persistent data storage that's associated with it, and that's called the key value store. Fabric also supports notions of confidentiality and privacy on transactions. Confidentiality is achieved by using encryption-decryption techniques, while channels are a privacy construct. Channels enable construction of private ledgers between some independent set of entities within the larger consortium. So if you have a private channel between, say, 3 organizations in a 16-organization consortia, then 3 of them can transact privately without the others finding out what the transactions and the smart contracts are on that particular blockchain. Let us look at a typical transaction flow. You have clients initiating invocations of chain code methods, okay? So the client generates something called an endorsement proposal, which is invocation of a certain chain code method along with the payload. And of course, there are certain security parameters associated with it. The endorsement proposal is sent to endorsing peers. This is dictated by the endorsement policy of the chain code. And the endorsing peer is responsible for validating the transaction, simulating and executing it, verifying the read-write sets, and either validating it by generating a valid endorsement or rejecting it. So the endorsement peer sends the endorsement response back to the clients. After obtaining the required number of endorsements, the client constructs a transaction and sends the transaction to the ordering service or the orderer to be included in the block. The ordering service then does its own checks and includes the block in the blockchain by sending it to all the committing peers that are present on the channel. The committing peers do their own checks and include the block within the blockchain, and this is how the blockchain is collectively maintained. The peers, in addition, are also responsible for generating events. This is how clients find out that a certain block is confirmed on the blockchain, and the clients, in turn, can respond to the confirmation event. So at Persistent, while we were building proof of concepts for different applications, we had certain natural questions that came up when we tried to transition from the POC world to building real-world applications. So we wanted to have a sound understanding of what the throughput of a certain system would be, what kind of transaction latencies can we expect. And similarly with application design, we wanted to know how certain design decisions would affect performance. And naturally, we also had scaling concerns because we didn't know what was the number of chain codes or channels or peers we were able to support with a certain kind of deployment. So putting our heads together and striving for answers to these questions, we came up with performance benchmarks, which can largely be categorized into 3 categories: control workloads, micro benchmarks, and scalability tests. Control workloads help us answer the larger questions about the deployment, what are the throughput and latency numbers for different kinds of workloads and order and chain code settings. Micro benchmarks help us answer what kind of influence certain transaction and chain code parameters can have on transaction latencies. And scalability tests, of course, address our scaling concerns. So let me talk a little bit about how we set up our tool, which is, by the way, open source and can be used by the community. The link is towards the end of the slides. It's called Gauge. We have a bunch of configuration files that need to be set up for the specific benchmarking, your specific Fabric deployment, and that is picked up by the load generator. The load generator can interpret this and generate a specific set of transactions which will load your Fabric network, which is on the far right, in a certain way that you expect it to. So it, of course, uses the Fabric SDK to create those transactions. We have a resource monitor, which is able to record CPU and memory usage on the peers while the experiment is running. We have a block event listener, which simply listens to confirmation events, confirmation of blocks on the blockchain. And there's a TPS and latency calculator, which does the calculations for throughput and transaction latencies. More details are in the paper. So I'd like to mention here that we initially forked this code of Caliper, which was open sourced by Huawei Technologies, which is now part of Hyperledger Caliper, and there is some stuff going on there. But when we started experimenting with it, we found that the original version didn't scale for very large input workloads, so we had to modify it to split it up into separate processes, and that's why we introduced this concept of messaging queue, where different processes could communicate by capturing transaction confirmation events and timestamps, and there was a separate process which could then do the calculations. So this tool itself, Gauge, is run on all the clients, and all the measurements are done at the client. So in the rest of the talk, when I talk about experimental findings, I just like to mention quickly what experimental setup we used. So we had 2 organizations, Org A and Org B, contributing 2 peers each to the blockchain network. We had another organization C, which was running the order, and we created a channel and deployed chain codes on this specific channel. The chain code had an endorsement policy that at least 1 peer from organization 1 and 1 peer from organization 2 has to endorse every transaction. The clients, we use 4 different clients, which would distribute the transaction load on all the peers. All the experiments were done on hardware in our lab on a local network. So this was the general experiment setup used in most of the experiments. There are few exceptions. The scalability ones especially are done on AWS because we needed access to more machines. So these details are noted in the paper. So the first set of experiments, which was control workloads. So we use read-only workload, write and mix workloads, and the null workload. The read-only workload simply reads off the chain code for a certain key. And this typically doesn't generate a transaction on the network the way Fabric is built, because it is serviced locally by the peer that receives the transaction. The write and null workloads generate a transaction and go through the 3 phases of endorsement, ordering, and commitment. The only difference between them is that the write workload updates the state of the key value pair, while the null workload simply returns. And mixed, of course, is a 50-50 mix of read and write. So what we notice in this particular experimental setup is that read workloads scale linearly as expected. The write and the null workloads scale linearly up to a transaction rate of 1,000 transactions per second. So what you see here is on the x-axis is the input transaction rate, And on the y-axis, for the two graphs, you have the transaction latency and the transaction throughput. So after that, the curve sort of flattens out and declines a little bit. The mixed workload neatly falls somewhere in between the read and the write workloads. So while investigating why there is a drop in the throughput after a certain point, we realized that the orderer parameters have a significant influence on the transaction throughput as well as the latency. So you can tune the orderer parameters, typically the batch size and the timeout, and you find that there's a variation in the throughput and latency. So what you see here on the left-hand side is the input load, and in the middle is the batch size. So if you increase the batch size up to a certain point, you see an improvement in throughput, but you cannot keep increasing it further because that would result in increased latencies as well as drop in the throughput. So clearly here there's a trade-off between throughput and latency, and this needs to be tuned correctly based on the application requirements. Similarly, the chain code endorsement policy has a significant impact on the throughput and latency. So it can be intuitively expected that if you have fewer number of endorsements, then you probably have an improved throughput and a decreased latency. But we wanted to quantify this impact, so we ran this experiment where there were chain codes which require a single endorsement and another one with 2 endorsements. So what we see here that up to an input transaction rate of 1,000 transactions per second, it doesn't make any difference at all. And only after that, when the load is increased further, the one with the single endorsement does much better. So with micro benchmarks, we wanted to tune different transaction and chain code parameters. With micro benchmark 1, we are able to change the read-write set sizes. And as you can see from the table, these are experiments done for different data points when the read-write set sizes have different number of entries. And the last column there shows the total latency in seconds. The latencies are broken down into 3 stages. C2E being the time taken for the client to send an endorsement proposal and receive the appropriate endorsement responses. E2O is the time taken for the client to send the transaction to the orderer and receive an acknowledgement, and O2E is the time taken for ordering and commitment as measured on the client. So as you can see from this experiment, as the read-write set size increases, most of the time is actually spent at the endorsement peer in running the chain code and generating the read-write set. So again, this is more or less expected, but here it is quantified by this benchmark for your specific input. With micro benchmark 2, you can alter the chain code and event payload sizes. So table 3 above shows chain code payloads, while table 4 shows the event payloads. So as you can see, as the payload size is increased from 1 megabyte to 40 megabytes, there is significant increase in the transaction latencies. With micro benchmark 3, what we wanted to understand is how key value store sizes affect transaction latencies. When you deploy an applications, key value stores typically tend to grow in size over time. And what we have here is we have the read latencies and the write latencies recorded for different size key value stores in the chain code, ranging from 1,000 to 1 billion, okay? And for read latencies, we see that beyond 100 million, when there's a jump from 100 million to 1 billion, there is a significant increase in read latency, but it's still in microseconds. For write latencies, this is mainly dominated by the 3 phases of yeah. It's in entries. Yeah. Yeah. With micro benchmark 4, you can measure the chain code to chain call execution overhead. So this particular micro benchmark, we were trying to understand which design works better. Should you include all methods in a single chain code? Clearly not a very modular design, or should you split it up across chain codes, and whether there is any effect on performance. And we measured this for call depths of 2 to 4. by including functions within a single chain code versus splitting it over multiple chain codes. And clearly there is an overhead for additional chain code calls. For the scalability part, we increase the number of chain code. The goal here was to try and find the system limits. Okay, so what is the maximum number of chain codes that a particular deployment can support? So in our experiments, we were able to have maximum chain codes, deploy maximum of 1,000 chain codes, but not all of them were invocable. Okay, so on the x-axis here, you see the input transaction rate. So for a certain input transaction rate, it was parallelly sent to all the chain codes to stress out the resources on the peers. So there's a steep drop in performance when resource limits are reached, and this threshold is lower than the maximum number of chain codes that is deployable. Similarly, we did an experiment trying to understand how many channels we can deploy on a particular setup. So for our setup, we were able to deploy around 450 channels, but not all of them could be invocable. Okay, so there is clearly a channel overhead with multiple channels, and with this setup, the performance actually drops a little when you compare it with the single channel scenario. The last scaling experiment was to try and increase the number of organizations to understand how throughput and latency is affected when you have large consortiums. So we went from 4, 8, 12, and 16. These were the 4 data points. And clearly, when you compare the throughput of 4 organizations versus 16 organizations, there is a large difference. So the catch here is that we accordingly also scale the endorsement policy. So in the 16 organization case, we had a requirement for 16 endorsements, which is clearly not scalable. So one has to keep that in mind. If you have larger consortiums and you want all consortium participating, there's a trade-off between security and performance. So to summarize the key insights, tuning order and chain code settings improves throughput at high send rates. So it's important to play around with these settings to figure out what kind of performance you're getting from a certain deployment. Transaction latencies are significantly affected by read-write set sizes and event and chain code payload sizes. Application designers have to be careful about how much, what the sizes of payloads are in this case. Read-write latencies are relatively unaffected by the size of the key value store, so designers have enough flexibility while trying to design larger key value stores and don't have to worry about it much. Interchain code calls incur an additional overhead of 5.2 to 7.45% on an average for each added level of call depth, posing a trade-off between modularity and speed. And finally, the scaling experiments help you test the limits of your system. It's important to understand what is the maximum number of chain codes, channels, and peers are supported by a given configuration before deploying real-world applications. And these were actually preliminary experiments, I would say, and in the process, we actually have ended up with more questions than answers. So I hope that this serves as a starting point, and we are all able to learn as a community and scale much better than just as performing all the experiments. So we've open sourced this tool. It's called Gauge, as I mentioned before. It works out of the box for Fabric 1.1 and Quorum 2.0. So we've tested it for both, and it works well. We actually have a paper on Quorum performance characterization as well, which should be out soon. This whole framework is extensible, and it can support other enterprise platforms with similar architecture, but you need to write a plugin for it, and it should work. And most importantly, Gauge can be run with customized settings. So you can have your specific blockchain deployment, your custom order and chain code settings, your consensus algorithms, and you could run the specific test to get the numbers that might be of interest to you. This is open source and available on GitHub at github.com/persistentsystems/gauge. And finally, I'd like to thank the rest of the team who contributed towards the paper and open sourcing the tool. Thank you. With that, I'm open to questions.
Does the delaying messenger queue is also calculated into latencies?
Sorry, say that again.
I mean, does the delay, does the time in relating messenger queue is also calculated into latency?
No, it's not. It's not, yeah. So it is. It contributes to the calculation time when the experiment is over, but it doesn't contribute to the actual transaction latency that is calculated. Yes.
When performing the benchmark test, did you experience any kind of consensus issues during tests?
Not with Fabric, but with Quorum we did. Yes.
So the key value store, have you developed it yourself or did you use some standard key value store?
We did the pre-population ourselves. So for 1 billion data point, it took almost 2 days to just pre-populate the key value store.
Any further questions?
Thank you.
Just one question. Your results were from Hyperledger, right?
Yes.
How do they differ from the Quorum results?
Quorum has different consensus algorithms, and well, I wouldn't make a direct comparison at the moment because these tests are of Hyperledger Fabric 1.0, which was the original production grade version. Now Fabric has 1.1 with a lot of improvements in performance, so we haven't done a head-to-head comparison with 1.1 and 2.0. So it wouldn't be fair to make a statement.
Okay, thank you.
Yeah, but you could do the comparison yourself. So download the tool. We'd be happy to hear from the community.
Thank you.